Thank you very much for joining us today for the Embodied Cognitive Science Seminar Series. Today we will have two talks. The format will be then 20 minutes for each talk, followed by a 20-minute discussion. And as always, we will pause the recording for the discussions. For the first talk, we are happy to welcome two speakers, Gaurav Patil and Nalepka. I hope I pronounce your name correctly. Please correct me if it's wrong.
Perfect.
Thank you. Dr. Patil is a postdoctoral research fellow in the School of Psychological Sciences at the Macquarie University in Australia. His current research is focused on modeling the dynamics of cooperative and competitive human multi-agent task performance. He is particularly interested in analyzing complex human movement behaviors, developing artificial agents which can model such behaviors, and evaluating the effect of artificial agents on the dynamics of human-agent interactions. Dr. Nalepka received his PhD in experimental psychology from the University of Cincinnati, where his research focused on investigating the perceptual motor processes that underlie the emergence of stable coordinated patterns in complex and dynamic multi-agent task context, as well as the role of constraints that play in how such patterns materialize. Since joining Macquarie, his focus has been on investigating the effects of embodied artificial agents, for example, virtual avatars, robots, and so on, that have mixed human-artificial agents teams for coordination, and how such artificial systems should be used to enhance human skill acquisition in perceptual motor task undergoing continual perturbations. Together, they will present a framework for modeling human joint actions using dynamical perceptual motor primitives. Dr. Patil, Dr. Nalepka, thank you for joining us today. Please take it away.
Awesome. Thank you so much for the introduction. And I hope the screen sharing is working. Everyone can hear me. Perfect.
We're good.
Okay. So thanks for the introduction again. My name is Gaurav. I have Patrick here with me. We are office mates and we are both in Sydney, Australia. So in this talk, we are going to give a brief overview of our modeling work in various multi-agent tasks. So before we do that, I just want to mention why we are interested in this work, basically why we are interested in modeling human joint actions. So basically, first allows us to understand the perceptual cognitive processes that underlie these complex behaviors. Additionally, we can also create artificial agents which can behave in a human-like way, and we can use them to replace humans in certain scenarios. Like we can create training systems which can provide skill learning in various tasks. So before we get into the specifics of the tasks that we are going to talk about, let's look at what the literature says. So from literature, we know that human motor behavior is intrinsically functional rather than intrinsically mechanical and extrinsically or secondarily functional. This means that the realization of the motor behavior and the dynamic order of coordinated activity is distributed across the agent environment system and not just limited to the agent. It basically means that as scientists, we can't observe actions in isolations, and we have to observe the agent environment system as a whole. The same applies to multi-agent task context. We cannot observe the actions of individuals in isolation, but need to study them in relation to the states of the environment and their co-actors. So when we look at an agent acting in an environment, research suggests that the agent's actions are not independent and they are more of a resultant of the affordances offered by the environment and then the constraints and the synergies of the musculoskeletal system. So for example, when you try to reach for an object, the object's position determines how you reach for it. Similarly, in multi-agent tasks, the other agent's state also affects your action. So basically, if your friend is passing you an object, the location of their hand determines how you reach for it, or even if you reach for it. So because of these constraints, these couplings are formed between the agents and the environment. These couplings can be either physical or they can be informational. So if your co-actor communicates some information to you that will affect your action. Additionally, these couplings basically result in an emergence of behavioral dynamics, and any modeling approach that tries to capture all of these needs to address both the couplings and also this emergence of behaviors. So let's start by looking at how to model simple human movements. From research, we know that most human movements can either be classified as discrete or rhythmic. So for example, reaching for an object or throwing a dart is a discrete movement. Waving your hand or hammering a nail would be a rhythmic movement. So these movements can be modeled by, or one way to model these movements is by using these simple point attractor and limit cycle equations, and applying these equations to model human motor behavior. Basically, we call them dynamical perceptual motor primitives, because these equations can be tuned or combined to create more complex movement patterns. So you might have noticed that the point attractor dynamics equation looks similar to this mass spring dynamics equation. So it basically has a mass term, or the acceleration term, it has a damping term, and then it has a stiffness term. The stiffness term basically attracts you to a goal. So if you set a goal or goal position, the stiffness term would attract you to it. The damping term basically opposes this motion. And then by varying these values, you can get different behaviors from the same equation. So you can either get a very overly damped system, then you can get something which looks like this. And if the damping is non-existent, then you get more of oscillations. The limit cycle equation is just a forced spring mass damper equation, as you can see here. And it can also be represented by adding a nonlinear term to the same spring mass damper equation. An interesting thing that happens in this equation is, instead of being attracted to a single state or a point in the state space, you basically get attracted to a closed trajectory in the state space. So basically from any initial point, you would end up in an oscillatory behavior. Additionally, by changing this, the value of the damping term, you can, this system shows bifurcation. So you could get both point attractor and limit cycle behaviors from the same system of equations. Okay, so moving on. So we are, how do we apply these dynamical perceptual motor primitives to model human behavior? So we are going to talk about 3 different examples. So first is just a competitive task, which is air hockey. Then there's a cooperative task where people move objects from one side to other. And then there's the cooperative herding task. An important aspect to applying the dynamical perceptual motor primitives to modeling these behaviors is also identifying the action. So basically what we call the action selection. So in the second example, it would be what object to pick up, or if to pass or drop off an object. And it will get more clear as we go through all of these examples. So first example, just a simple air hockey. Well, it's not as simple as you would think, because recording data in such a fast-paced game can be really hard. Unless you have a camera which can do more than 500 hertz, you can't really get the puck's position and capture the position in every frame. So that makes it really hard to model the behavior in air hockey. So we decided to go with virtual reality, because then we can do whatever, we can basically move the puck around and record the data as we want. Another challenge in VR is actually latency. So we can't really have 2 human players playing this game in VR. So we basically had to use this task in a single player version. So we had to have the humans play with some artificial agent, record that data, and then tweak the artificial agent. And finally, the expert versus novice gameplay is very different. So you can see in the left video how the novices just keep on hitting the puck, whereas the experts kind of make the puck, like take possession of it and then tactically try to move it in the opponent's goal. So that makes it a bit difficult to model the expert gameplay. So yeah, just to keep something in mind. Apart from the challenges, the good things about this task are we know that the movement dynamics are quite simple. They are just coupled point attractors. So as long as you know the goal location, you can just use the simple point attractor behavior to go there. And then actions are quite simple. You either hit the puck or go to a home location and try to defend your own goal. So how does this translate into actual equation? And before I go to the next slide, this is our task setup. So we have a table, a participant in VR, and then that's how the table looks like in virtual reality. Okay. So how do we model the behavior, right? Okay. So first, of course, we are we were limited to just doing human AA gameplay. We couldn't really do human-human gameplay. So we decided to create a simple artificial agent, which we call the preliminary model, because it had very simple action selection rule. Of course, the movement dynamics were modeled by the spring mass damper equation in both X and Z direction. And then the action was basically you hit the puck if it is on your side and you defend if the puck is on opponent's side. We also coupled the defensive motion to the puck or lightly coupled it. So you kind of get this interesting behavior as if they are trying to defend the goal. So here's how it looks like. Doesn't really look that human-like. And it's quite easy to beat this preliminary model. And that's what we saw when we had participants play with this agent. So we saw that almost all participants defeated this agent. They really crushed this agent. I think almost 95% of the trials were won by humans. So doesn't bode that well for our agent, but at least gives us some data to start improving our model, right? So I'm not going to go too much into detail about the behavioral differences, but they are in the latest CogSci paper, which I think I have it somewhere, but yeah. So based on what we saw in the initial trials, we modified the model. So instead of just having it hit the puck when it is on their side, we also coupled it to the velocity of the puck. So if the puck was moving faster, they were more like, the agent was more likely to defend. And if the puck was slower, they were more likely to hit. And this is still work in progress. We are, as I talk, we are collecting data with this new model and trying to analyze it. But just from the preliminary findings, it's really hard to beat this improved agent. And the only improvement was the slight change in the action selection. In addition, by just looking at the behaviors, the behavior of the agent looks more closer to the human behavior than that of the older agent. Okay, moving on, the second task I'm going to talk about is the object pick and place task. This task is also presented to participants in VR. Fortunately, we were able to get human-human data, so it makes it much easier to model the behavior. So in this case, two agents stand opposite to each other, and we use the same table from my earlier picture. Objects appear in dispensers on one side of the table. The task is to basically pick the object and either pass it to your partner or drop it off on the other side. And this is how the task looks like in VR. You can see how the objects are in the dispenser and then they are to pick them up and drop them off on the other side. There are also two different conditions in which the objects appear. They either populate all the dispensers at the same time, or they appear one at a time and a new object doesn't appear until the older one is dropped off. So how do we model the behaviors in this case? So first thing was that we observed people were more likely to pick up the objects that were closer to them. And when we also reach normalized the distance of the objects, they were more likely to pick up the objects, by which I mean that when an object appeared in the central dispenser, a taller participant was more likely to pick it up than a shorter participant. The same with the drop-off location. So if the drop-off was in the central collector, taller participant was more likely to drop it off, and which also determined if the object got passed or not. And then there were specific locations at which the passes happened. I'm not going to go too much into detail, but you could look at the latest CogSci paper for this. Okay, so modeling this behavior, the movement dynamics are quite simple. They are again coupled point attractor. If we know an agent is going to pick up an object, we can just use the spherical coordinate system and then the spring mass damper systems and get this movement. The action selection is a bit complicated. So we use this affordance based model where basically if an object, and as I said earlier, if an object is closer to you, you are more likely to pick it up. And then this function, which basically exhibits a saddle node bifurcation. So depending on the alpha value, it either basically gets attracted to this point or gets attracted to this point, and that determines who picks up the object. So by implementing these equations, we were, this is just a demo of how the agent plays or completes the task with a human participant. If I can see it. There we go. So this is the single object condition. And you can see that the agent decides, and the first person view is the human, and then the agent is the one on the other side of it. Yeah, the agent really doesn't like to pick up the objects in the central dispenser, but maybe because it was a taller participant playing with them. And then this is the multi-object condition, and you can see that both the agent and the human participant can complete the task successfully. And then the interesting part is where they can actually swap the objects in between. Yep, and that's it for me. I'm going to pass it on to Patrick now, where he's going to talk about the herding task.
Yep, so just stop screen sharing, Gaurav, and I can switch over.
Yeah,
yep. Thank you. Good, share. Good. Give me a thumbs up if you see my screen. All right, good. Okay, cool. So as Gaurav mentioned, complex perceptual motor behavior can be decomposed and modeled using these fixed point and limit cycle attractors. And so for a third example for how we can utilize these elementary building blocks to kind of describe complex human behavior, the example that I've worked with during my PhD studies and during my postdoc years is this collaborative problem solving game that we call the human shepherding task. And what this task is it's a video game where participants have to, while standing on either sides of a table, using motion controllers with the right hand, they control these little cubes that you see on the right side of the screen here. And what participants have to do is work together to find some sort of solution to corral and contain this set of invasive agents that you could think of as like sheep. This is why we call it the shepherding task. Just to kind of illustrate the basic behaviors that we see in strategies that we see teams adopt. The first strategy, which is what everyone adopts, is what we call search and recover, where here participants will implement a strategy where they subdivide the task space in half. There's a my side and your side, and each participant basically pursues the sheep that's farthest from the goal and brings it towards the center. Where here the goal again, if I forgot to mention, is to keep them all within this red circle. When task difficulty increases, so we throw in more sheep that they have to corral, this strategy is not very effective. And so participants will either fail at solving this task, but for those who don't fail, what we see is that a new strategy emerges during the course of this game, where instead of worrying about each individual sheep and how they should go about pursuing them, participants realize, oh, hey, who cares about these sheep? Let's just oscillate together. And by forming this type of like circular wall around the entire herd, participants who discover this strategy reach near ceiling levels of performance. And so you can implement either this kind of in-phase rhythmic coordination-like behavior, and you also see anti-phase rhythmic coordination behavior too. And if you are familiar with interpersonal coordination literature and just rhythmic coordination or the coordination dynamics literature generally, in-phase and anti-phase are the two stable modes that we see in interpersonal coordination generally. And then also the relative, what's the word? The probability of which state is emergent is consistent with theory, such that what I mean is basically that in phase is a more probable coordinative state than anti-phase, but both are stable modes of behavior here. So we call this coupled oscillatory containment on the right side here. Gaurav mentioned in the beginning that kind of what we can do is exploit this concept in dynamic systems theory of hot bifurcation, where again, a hot bifurcation, what that is a dynamical system which exhibits kind of point attractor behavior, fixed point attractor, so there's a clear defined goal. At some point when you scale a control parameter, what ends up happening is that the stability of this attractor decreases to the point at which a limit cycle behavior emerges. Using this as an example, we can relate it to the shepherding task such that search and recover behavior, we could think of as point attractor control, such that each target is the end goal that the player has to move towards. And that at some point, participants then switch from, instead of pursuing individual objects, they go around the entire herd. To model this, our workhorse is the second line here, which is a nonlinear oscillator, which controls the angular dynamics that we see here. Here we use a polar task coordinate system, such that what participants are doing is controlling the radial component as well as the angular component here. And you can define kind of an information control law here, I guess you can think of it this way, which is tied to the distance of all the objects to the center of the field, such that when the spread of the targets is far, what this model does is implement this fixed point control. And then once the targets are kind of close together, it produces this hot bifurcation effect here. And then we see these oscillatory behaviors. And we've tested this model with an artificial agent. You see more of the details in this 2019 paper here. Where on the left side here, we see two novices who discover this oscillatory type behavior. And on the right side here, we see in orange a novice participant working with an artificial agent, which implements this model. I skipped over most of the details of the model. You can ask me later. But we've also done this kind of like Turing test kind of situations where we bring participants in to do this task. And we tell them that their partner is a human participant, where in fact it actually is this artificial agent. And what we find is that most participants remain in the belief that they think that their partner is human, although it's this AI agent, which provides some evidence that these models consisting of these dynamical motor primitives, although aren't exactly like human movements, seems to kind of share the key features of human behavior. And I think we're running out of time, but the last thing I'll touch on is this concept of dynamic similitude, where, as I mentioned before, the coordinate behaviors we see in this shepherding task shares the same types of dynamics that we see in the rhythmic coordination literature generally, going back from interpersonal coordination of finger wagging to coordination of pendulum swings to an environmental stimulus, such as an auditory metronome, or the coordination of limbs between people. And in all these situations, despite the differences and the constraints acting upon all these systems, the same types of dynamics emerge. And similarly, in this kind of shepherding task we developed, if you look at collaborative hunting generally in non-human systems, the same types of strategies emerge within these systems, despite the constraints acting upon them, which is the key is, again, this kind of encirclement of prey. So wolves do this, whales do this. Participants in our experiment form this type of wall around our little spherical sheep. And so we wanted to also explore the extent to which these dynamical models that we generate and create could also translate to different these different disparate task contexts. And the way we started doing that is actually transporting this shepherding task into a full body locomotion-based study, where we moved away from this video game where people move a controller with their hand to now actually fully embody, like moving around an environment, still, treating it like, imagine the cow as a sphere, imagining sheep as a sphere. So the graphic is kind of low due to my lack of skill in 3D animation, but still kind of bringing it closer to possibly, what we may see in a kind of more realistic context. And what our prediction was is that, given it's the same task, just in a different context, that the same types of strategies should emerge. But what we see instead is that instead of participants learning to oscillate around the herd as an effective solution, what we see instead is that participants learn to actually perform these circling motions around the herd itself. Not everyone discovered this, but this is kind of this task's equivalent of this kind of eureka aha moment, which participants discover with the tabletop condition. And so to make sense of the differences in the observed behaviors within these different task contexts, we can still exploit the same dynamical models that we've been talking about throughout this entire talk to kind of uncover kind of how these strategies come about. And specifically, we could use minimal models, so kind of novice level models of behavior during the shepherding task. And we could play around with the parameters within those functions to kind of recreate the constraints acting upon participants in these disparate task contexts. And just quickly, basically what we see is that even these very minimal novice acting agents, what we see is that these expert-like behaviors are emergent properties of this task. So on the left side here, these agents actually don't know how to oscillate, but based on the dynamics of the task environments, animal environment system, these oscillatory behaviors nevertheless emerge. And similarly, when we re-parameterize the model so that kind of the movement dynamics are more emblematic of what we see in the locomotion case, instead of oscillating back and forth like that, we see that these agents are actually now spinning around the entire herd itself. And the summary here is basically, I'm going to use a different graph than what Gaurav used, but this is from Warren's 2006 paper, where we can use these task dynamic models to define, basically formalize, provide like a mathematical formalization of what the task is, which then constrains animals' behaviors within their environment. But then by that ongoing interaction, this kind of animal environment interaction, new information could be generated, which then informs and kind of evolves the graph or the task dynamic graph that we use to model the task generally. And then just in closing, the work we're doing now in the future is supplementing all the modeling work we're doing with kind of, all the cool, sexy stuff that's happening in the artificial intelligence community, specifically to the extent to which we can supplement our models using artificial neural networks to help develop more flexible decision-making policies, as well as exploring methods in deep reinforcement learning or supervised machine learning to train artificial agents either on human data or from scratch, and then using explainable AI techniques on those systems in order to discern kind of the informational variables that agents may be using in making their decisions in the task environments. And that's pretty much it in closing. That's all of us. Might have gone over, apologies, but thanks everyone. And we'll take any questions you may have.